and liftoff.
Welcome to a new episode of Kleos Insights. Hi, Rami.
Hi, Federico.
Tell us a little bit about your background and what has led you to join Kleos.
Yeah, sure. I have a PhD in signal processing and a Master of Engineering in digital communication. Before joining Kleos, I used to work in the aeronautical and the defense sector. I worked as a signal processing engineer in the signal intelligence context. So usually my work starts after the, let's say, analog to digital conversion of the signal. So I'm working on the digitized version of the radio wave. My work involves designing reception algorithms, as an example, synchronization, demodulation, decoding algorithms, and signal identification. I also have a background in geolocation. And in Kleos, I'm combining both my knowledge in geolocation and in digital communication because we are geolocating RF transmissions from space. So I'm using both expertise on a daily basis to design the geolocation system because you need to know, let's say, the characteristics of the signal that is transmitting, and also you need to know how to geolocate them.
So you mentioned geolocation. There are two kinds of geolocation. So we have the passive geolocation and active geolocation. Please guide us a little bit defining geolocation through the examples of passive and active, then the differences.
Of course, yeah. Let's maybe start first by defining what is geolocation. So geolocation is the process of identifying a target's location. And the classification between active and passive is dependent on the nature of the target that is being geolocated. So in the active mode, the target has access to some information that is needed to perform the geolocation process, like the transmission time, the Doppler, etc. So the target usually is synchronized with the other device that is used also for geolocation. And in the passive mode, the target is uncooperative, meaning that so the sensors that are used to geolocate that target do not have prior information about the target, especially the transmission time, for example.
Understood, clear. So now speaking about techniques, which are the techniques that are currently employed for passive and active geolocation?
Yeah, so there are so many techniques that already exist and are developing every day. To start with the active geolocation, maybe we can take as an example the legacy global navigation satellite systems, so the GNSS. Almost everyone is using the GPS systems. And the GPS system is considered as an active geolocation technique because the target, which is typically a GNSS receiver, has access to some information like when the signal is being transmitted from each GNSS satellite, and using that information and by knowing the reception time, the GNSS receiver can estimate the distance between the receiver and each satellite. This distance is known as the pseudo-range. It's not the real distance because the estimated distance is biased by another parameter, which is the clock bias. So by using those pseudo-range measurements coming from different satellites and using trilateration, the receiver would estimate its position based on those information. In our context, which is the passive geolocation context, we do not have that kind of information. We do not have a prior information about the target. We do not know when the target has been transmitting its signal. So instead of using that information, we are using the fact that the signal is being receptioned by multiple spacecraft at different times. So instead of computing what we call the time of arrival, we were going to compute the time difference of arrival, which is basically the difference between the two time of arrivals relative to two spacecraft. And by this way, we don't need to know when the target has been transmitting the signal in order to do the geolocation. In a similar way, we can also use the Doppler effect since the satellites are moving relative to the target. So when we talk about target, we're talking about ships, users that are using walkie-talkies, things like that. And what we call the Doppler effect is basically is translated as a frequency. So the signal is received at multiple frequencies at different spacecraft. And basically using that information, we can also estimate the frequency difference of arrival. So by using the time difference of arrival, the frequency difference of arrival, we can also use other measurements if necessary. These measurements are related to the target's position via a system of nonlinear equations. And by resolving that system of nonlinear equations using some estimation techniques, advanced estimation techniques, we get the target's location.
Thank you. That was quite a piece of information. But following up, I think, correct me if I'm wrong, the next step is to define accuracy, because geolocation needs to be defined according to an accuracy.
Yes, of course. That's a really great question, because we need always to tie geolocation to accuracy. It doesn't make sense to geolocate something if the accuracy is very, very bad. So basically, there are two main factors that impact the geolocation accuracy. The first factor is the measurements errors. So when I talked earlier about TDUA and FDUA, these are estimations of the time difference of arrival and the frequency difference of arrival, and they do not necessarily correspond to the true time difference of arrival and the frequency difference of arrival. Why there is such a difference? Because there are some errors that are produced by either the inherent characteristics of the signal that we are using. Please keep in mind that we are geolocating a signal that has not been designed for geolocation. It's more like designed for communication. So it does not have the attractive characteristic that we want to have for geolocation. So that's one factor. The other factor is the propagation effect, the fact that we are detecting signals from space, so we have low signal to noise ratio at low elevations. So these are, let's say, the main effects that impact the measurements. But there's also another factor that impacts the geolocation accuracy, which is the geometry. So the way how the spacecraft are spread above a given area of interest or above the target has a direct impact on the geolocation accuracy. The geometry effect is translated via a mathematical model or representation called the dilution of precision, the DOP. We can see the dilution of precision as a scaling factor that is going to convert the measurement errors that we've talked about earlier to positioning errors. So the lower the DOP value, the higher the accuracy we can get. Or also we can say the better the geometry, the lower the DOP value we have. And the better the geometry, the geolocation accuracy we're going to get.
Okay, so you are linking geometry to accuracy.
Yes.
So let me ask you another question related to geometry. Does the number of spacecraft, included in the cluster geometry, have an impact on accuracy?
Yes, of course. Basically, the more number of spacecraft we have, the better the overall accuracy we get, because we will have a better geometry, especially when we are targeting low elevations. So the fact that we have 4 spacecraft is going to give us a low DOP value over a given area of interest. But also the fact that we have 4 spacecraft is going to affect the measurements as well. So the first factor that I talked about earlier, because since we are detecting the signal using 4 spacecraft, we will have, let's say, a more statistical reliability of the measurements that we are doing. And the more reliability we have, the less errors we will get, and the better the geolocation accuracy we will have.
Thank you. So now we need to close the loop. We started defining geolocation, we started talking about passive and active geolocation differences, and then we touched base on techniques, but also on accuracy, which is a very important parameter. The final question to close the loop is, for a given position estimate, how can we really be sure that a target, a transmitter is there?
Yeah, that's an excellent question, because basically when we give key performances about accuracies, when we provide the geolocation estimates, we provide what we call confidence ellipse. That confidence ellipse actually gives the surface where the transmitter really is compared to the estimated position. And this ellipse is computed by taking into account the factors that I was talking about, the measurement errors and the geometry of the spacecraft. To give you maybe an example, in the white paper, for example, we've done a capture of using KSM-1 over the Cape Verde region, where we have a controlled beacon that is transmitting a signal at 4.2 watts. The true position of the beacon is inside the ellipse of 4.5 kilometer semi-major axis and 260 meter semi-minor axis. And the center of the ellipse is the estimated position. So to answer to your question as well, it's true that we do not have beacons that are spread at every point on Earth, but by using mathematical models and using the ellipse concept, we can give a position with a confidence level that is going to indicate where the transmitter really is compared to the estimated position of that target.
Thank you, Rami. It was really important to listen to all these inputs you have provided us.
Thank you for having me, Federico.